So far, we've worked with arrays to store our data. Arrays are a linear structure with all elements stored in contiguous memory spaces. For example, a char variable size is 1 byte, so with an array of chars, each element is 1 byte over from the last. Because each element is contiguous in memory, we can quickly access a random array index with a simple calculation. So to access the address of the element at position n in an array, we take the address of the element 0, and we add n times the size of whatever the data type is. Doing a single math operation is a fast operation, so randomly accessing elements in the array takes virtually no time at all. As an example, let's say I want to access element 2 of this char array. Well, the address of the first element is at the memory address ending in A4. The size of each element is 1 byte, and we want the element at index 2. So we take the index 2, multiply it by the size of 1, so that's only 2 bytes over we have to move. We take the original address, go over 2 bytes, and that is where the address of the element at position 2 is at in the array. So again, the array of chars has each element 1 byte over from the previous. If we had an array of integers, integers are 4 bytes each, so in that case, each address is 4 bytes over from the previous one. As another example, let's say we want index 2 from an array of integers. The first element here is at address D0. The size of each element is 4 bytes, and we want the element at index 2. So we take the index 2, we multiply it by the size, which is 4 bytes. That means we need to move 8 bytes over from the original address. So our item at index 0 is at the address D0 in this case. Moving over 8 bytes, we then go to address D8, and that's where we want to be. When an array is full, however, we can't just resize it by allocating more memory in the original array. As a program runs, memory spaces are taken on demand, so the elements after the original array might already be taken. When we want to resize a dynamic array, we actually need to allocate space for a whole new array of a larger size. We then copy all the elements from the old array to the new array, and just update our array pointer to point to the new space. So, for example, here's an old array where we are out of space. It only has a size of 4. We allocate an array of size 6 elsewhere in memory, and then we copy all of the elements from the old array to the new array. And as far as the C++ code, we would actually delete the old array as well. So now we have space for more items, but if that fills up, we'll have to do another resize. And just as a note, these other things here are just other variables meant to represent that space in memory is taken up before, after, wherever. The process of allocating more memory and copying everything over means that anytime we run out of space, the program has to pause, resize the array, and then resume. This process is pretty costly since for n elements in the array, you have to iterate n times and do n assignment or copy statements. Another issue with arrays is that, to prevent having to do resizes too often, we have to overestimate how much space we need. This means that we're allocating space that we're not even using. So one of the good things about arrays is that random access is fast. We can access any element at an arbitrary index pretty quickly because all we have to do is a little math operation. On the other side, resizing arrays is costly, which means we have to allocate that new memory and copy everything over. And also, we generally will allocate more space than we're actually using. It's very rare where we will know exactly how much space we need to allocate to store some data. For some designs, maybe arrays are what we want. Perhaps in our application, the data is being accessed much more than it's being added to. However, what if we're not accessing the data very often, but we frequently add new data? Then an array is not very efficient. So there's another type of structure we can use. With a linked list, we only allocate space for one element at a time. Each element keeps track of who comes next, and maybe who comes previously. The list itself keeps track of which element is the first one, and it might also keep track of which element is the last one. So the big way it differs from an array is that we only allocate space for one element at a time as it's needed. Because everything is created as needed, elements of a linked list are in random places in memory. Each element keeps track of who comes next, and sometimes who comes previously. And we do this by using pointers. We make a special wrapper data type so that each element can point to the address of the next item in the list. And the list itself keeps track of which element is the first one and maybe the last one. So besides having a data type to wrap the elements, which we call a node, we also have the linked list data structure, which keeps track of which node is the first one, and maybe also keeps track of which node is the last one. So for a linked list structure, we have a list class and a node class. The list class contains pointers to the first and possibly last items in the list. And the list class also contains the interface, such as push, pop, and get, whether at the front or back or somewhere in between. And the node class is very simple, containing only the data itself for the element, and the pointer to the next item, and possibly the pointer to the previous item. If we were writing a singly linked list, it has nodes that only point to the next item, not the previous item. So here we can see a sample diagram where we have the singly linked list node. It has a constructor, it has the data, and it has a pointer to the next item. And as an example, the struct or the class for the singly linked list node would look something like this. For a doubly linked list, it has nodes that point to both the next item and the previous item. So in this diagram, we have the doubly linked list node. It has its constructor, it has the data, and it has a pointer to the next item and the previous item. And here is how the struct or class for this doubly linked list node could look. We're going to be using doubly linked nodes to learn with because it's easier, and once you know how linked lists work, you'll be able to figure out the functionality of a singly linked list more easily. The trade-off here is that you're using slightly more space to store a pointer to the previous item for more intuitive logic while coding, and I'm okay with that. The linked list itself contains the functionality to interface with the list and the necessary variables to implement the structure. As a note, some implementations of lists do not contain any functionality to access things in the middle, just the front and the back. But we are going to implement all three: push front, push back, push at, and the same for our pop and get as well. So let's look at the functionality of a linked list visually before we get into any code. With a node's constructor, when we first set up our node, it'll have some sort of data, and it's okay if that's garbage, we'll override it later. But the important thing is, since we have pointers to the previous node and the next node, and we're starting a completely blank node, we want to make sure that these are pointing to null pointer. So in the constructor, it'll be pretty simple. We just point that to null for both of those. We need to double check. And again, the reason why we like to set our pointers to null, if you don't remember, is that pointers can also store garbage data within them, so there's no way to tell what is a valid address versus an invalid address. So to stay safe with our working with memory management stuff, we set our pointers to null pointer because we can always see what is null pointer. We say, well, if this is currently pointing to null pointer, we can't work with it, it is not allocated anywhere, or it's not pointing to any memory, so it's a way we can kind of safeguard things. With the linked list constructor, when we have a brand new linked list with nothing in it, we should have item count set to 0, and again, we have 2 pointers to the first and the last item, or just one, possibly. You can have it just point to the very first item of the list and not the last. I like to do both, but either way, both of those pointers should point to null pointer to begin with. When we want to add something to the front or the back of the list, but the list is currently empty, we're going to just basically create a new node and set the first and last item to point to that one node. So starting off, this list is empty, and we would allocate memory for a new node. We'll bring that down here. We'll just have this as a copy for backup. And then we set its data. So we need to set it to cat, because push front here has cat. We are going to keep this one pointing to null pointer for its previous and next, because when we only have one item in the list, there's nothing before it, there's nothing after it. However, now we need to set the list's first and last pointer to point to our item in the list, our very, very first node. So that will set up that way. This is still fine as it is. And the functionality here for push front and push back is the same if the list is empty. But if the list isn't empty, then we have a different set of things we need to do. That pointer just helps us allocate memory, and then once we have it linked in the linked list, we don't need it anymore. It'll go out of scope. So that's for pushing front. Let's say we want to push to the back. And let's add rat. So we'll go ahead and we're going to allocate space for a new node, set its data. And now, because it's going to be at the back of the list for a non-empty list, it's going to go on this side. So we're going to bring it down here. We're going to set the next item of the current last. We're going to point it to the new last. So old last, new last. And again, new node is currently pointing to this thing, and that's how we would access it. Now, the new node's previous is going to need to point to the previous item. So let me kind of rearrange these arrows a little bit. So previous item is the old last, but we haven't updated this pointer yet. And then of course, the next item of the last thing is going to be null pointer. Last update, linked list is now going to point to this one as its last. And then this goes away. So that's what it would look like to push a new item, and it would be the same process every time we push back. We add another node down here. Every time we push front, we add another node on that side, on the left side. When we're removing an item with either pop front or pop back, and we only have one item left in the list, then the behavior here is also going to be the same. What we need to do is we're going to deallocate this memory, and so its members go away, but now this is still pointing to that old address. We need to have it point to null pointer instead. So again, we deallocate this memory, and these go away, but this is still pointing to garbage, so we need to then reset those two pointers to null pointer. Now, if we're removing something from the front of the list, but there are multiple items, we have more than one item in the list, we're not removing the last one, then we remove it, but we still need to update pointers. So what are we going to do? Well, we'll take the pointer first and point it to the next item. So what this would look like is we would have m pointer first is now equal to m pointer first's m pointer next. We're taking this thing, tracing this. What is this thing's next? That follows to this pointer over here. And we're updating m pointer first, or just pointer first, to point to first item's next item. So we point that there. We still have access to this node via the pointer previous. So then we free that memory with something like delete m pointer first, this new first node, it's m pointer previous. Delete the node that is behind it. So then that goes away, and we need to update some pointers. Update the pointer previous to point to null pointer. Likewise with pop back, if we're removing the last item of the list, we can again access this will be the new last item. So we can say m pointer last is now equal to m pointer last's previous item, pointer previous. So then we take, okay, here's the pointer here. We're saying the last is now equal to this thing's previous. So it goes here. Then accessing last items next. So we do m pointer last and its pointer next. That's what we're going to delete. So that gets deleted. And we update the pointer next here to point to null pointer. For the get front function of a linked list, we just follow the pointer first and return whatever its data is. So basically we would have return m pointer firsts data. Now, of course, if the list was empty, we'd want to throw an exception. We'll talk about error handling later on, but just as the basic data, we access the first item, we return that data. Likewise for the get back, we trace the pointer last. We'll say return m pointer lasts data, and that accesses this data and returns whatever that is. Now let's talk about accessing items in the middle. So again, if we have a get at function that takes an index, there's not really index numbers. These are not elements in an array. We would have to count and say like 0, 1, 2, 3, and so on. Now, not all lists will let you access something in the middle, but we're going to implement that to see how that works. So when we have something like a get at function, we're going to create a pointer. We're not going to allocate memory with this pointer. So there's something like, we could say node t new node is a new node type t. We're not doing that. This is allocating memory. What we're going to do here is we're pointing to existing memory. So we have node t pointer current is equal to the pointer first. So basically we can just set one pointer's address to another pointer, then they'll both point at the same address. So we're going to start here. We're going to just create a pointer. We're going to look at whatever pointer first is pointing to, and we're going to copy that over. So pointer current is going to start by pointing at the first item. We'll bring that down here. Then we're going to have some sort of counter variable. So let's say counter is 0. So if they said get at index 2, we would say, okay, we're doing a loop, a while loop or for loop. Are we at index 2 yet? No. Okay, so we're going to add 1 to the counter and move to the next item. And this will point here. And that code is going to look like pointer current is equal to pointer current's pointer next, or m pointer next, whatever. So we can access the next item just by using the pointer and its pointer to the next item. Now, does our counter equal 2? No, it does not. We're going to iterate again. So we'll add 1 to the counter and move it over. Now this is pointing here. And we'll look at, is counter equal to 2? It is. So then C is the data that would get returned. So that is how the get at functionality would work. So this behavior is known as traversing the list, where we have to start at the beginning and move forward by 1 each time, because we can't just randomly access. This list isn't pointing to any of the middle items, just the very first and last items. And so we have to start at the beginning and move forward, or we could start at the end and move backwards. It's not going to be any better. But we have to traverse the list to get to where we're going to go before we can do our operations. So with a function like push at, where we want to insert some new item at a certain position, we again would have to traverse the list to find the correct spot, and then we'd create our new data. This time we have a z, and then we have to update the pointers. So based on that, this goes here. We're going to push this over, but we have to update all these pointers to get it to work right. So I like to make pointers to store the before and after items. That's kind of extra steps. I just like to make my code really clear. But basically what we have to do, so we have pointer current pointing to the index where we want to add the next item. We're going to access the previous item before it and set its next item to our new node. So for instance, it could be something like pointer current, pointer previous, and its pointer next is equal to the new node. I know that looks really weird. That's why I add some extra steps in between, but we can see that later on the coding side. So let me make some space for this. This one right here, this is also, we're going to set its pointer previous to point to this previous item. So we're not really done yet. We still have all these other pointers. Now pointer current, this is going to be the new next. This is going to go after the inserted item. And maybe it'd be a little more handy if I made that a different color. So we're going to update pointer currents, pointer previous, to point to this new item here. And then finally, we need to set pointer next to that pointer current. So we've added an additional item. We also need to increment the item count. And now we've added a new item to the list. And again, with something like pop at, we have to traverse the list. We start at the beginning, that doesn't match. Add 1 to counter and go to the next item. That points there. That's where we're going to remove an item. And when we remove it, we need to update the pointers for the previous item and the next item, so we fill in that gap. So we free that memory. However, before we free that memory, we want to update the pointers, because if we just free the memory and these pointers are left dangling, it doesn't know how to get over here because we deleted all that information. So we update the pointers first. We say this is pointer current. We're going to take its previous item here is its next item's new previous. So again, that's why I make things a little bit longer in my code, but I have something like a node t before is equal to my pointer currents pointer previous, and I have a node t pointer for after as pointer currents pointer next. Then by doing that, I can put after's pointer previous is now before, and before's pointer next is now after. So I like to add these extra steps. I think it makes it much easier to read the code. You don't have to. You could write it like, okay, pointer currents, pointer previous, its pointer next is now equal to pointer currents, pointer next. But if that's confusing, if you have a hard time keeping track of that, just do it the easy way. So what we're doing is we have pointer current. We're going to get rid of this guy, but first we need to update this node to point here as its previous item. We need to update this node to point here as its next item. And these pointers here don't matter because when we delete this piece of data, those pointers go away. So then we have removed an item and we are shrinking our list. If we're not popping from the front, we don't really have to update any of the list pointers here. We're just updating pointers between the nodes so that they all know which one comes next, which one comes first. Okay, so let's look at the code for a linked list. Here I have my doubly linked list node. It has a constructor. It has a pointer to the next item and to the previous item, and some data. And we really just implement that constructor to set the pointers to null pointer, just for type safety. This is a templated class, and the linked list is also templated. Now in my linked list class, we have private member variables here. We have the pointer to the first item in the list and the last item in the list, and we keep track of an item count. Then we have our constructor and destructor, pushing to the front, back, and in the middle somewhere, popping from front, back, and middle, get from front, back, and middle, and then some other helper functions like display, which will display the elements to the screen, get the size of the list, get whether it's empty or not, clear out the list, and just a quick thing to check if it's an invalid index, if we wanted to access something outside of bounds. So we can first look at the constructor. We're setting these pointers to null pointer and initializing the item count to 0. Let's implement clear really quick because it's gonna not like it if I have my destructor and I've allocated memory, but the destructor can't deallocate anything. So for my destructor, I'm just calling the clear function, and then we need to implement clear. So basically, how do we free all the memory we're going to allocate? Well, while our list is not empty, we can just keep removing things from the front. Or we could keep removing things from the back, doesn't really matter, but we'll just say while not is empty, we're going to say pop front. And this isn't currently implemented, so we'll look at that later. Let's make sure is empty. Yeah, that's already implemented here. Okay, so let's start with the push front functions. we'll look at just the front-based functions. So for instance, with push front, we're going to need to think about a couple things. Are we inserting to an empty list, or do we have at least one item already in the list? So for this one, we'd need to do a check. But either way, whether it's the first item or the fifth item, we're going to need to create memory. We're going to need to allocate memory for our new node. So we can put this over here for reference as we work. But we need a new doubly linked list node of type T. I'm just going to call it new node, and we're going to allocate memory by saying new doubly linked list node of type T. We also need to set its data, so new node, its m data is equal to the new data passed in. So as an input parameter, the data that we are storing in the list is being passed in. The user doesn't care what a node is, what's inside the list. They just know that if, for example, they're storing a list of strings of employee names or whatever, they're just going to pass in a new employee name. They don't have to care that it's inside of a node. That's the point of our data structure. So we're going to say if is empty, then this is the one scenario we need to do. Otherwise, if it's not empty, we have a different set of things we need to do. And at the end, we will want to increment the item count. Okay, I have some drawings up here, but we'll just go with this. And again, I can open this up if we needed that for that visual reference. So, linked list when it's empty, pointing to null pointer for both its first and last items. I have went ahead and I created a new node of whatever data. We don't really care what this data is, but yeah, whatever. So this node, if this list is empty, we're going to set the first and last pointer right here. And that's what we'll need to do. And I'm just going to get rid of this item count because I keep forgetting to update it. So over here, we'll say m pointer first is equal to the new node, and m pointer last is equal to the new node. These are the member variables of the linked list. Okay, so I put these side by side so we can reference them both at the same time. Our linked list has the pointer to the first item and the last item. Not to be confused with the node, which contains pointers to the previous item and next item. So I will put this down here as well. Note that these are separate things. Next and previous, first and last. That's really easy to get mixed up because they both, for the doubly linked list, have a pair of pointers. So that's what we have to do if it's an empty list. Otherwise, if it's not the empty list, well, this is going to be our new front item. So if it's not empty, again, we have this. We've added a new node of some kind. We need to say this one's previous is now this guy. Point this one over here. Point this one over here. And of course, its previous is going to point to null pointer. So that's a little bit ugly, but I already went through this. So scenario 2, we're going to say m pointer first. This is referencing the old version of pointer first. Its previous item is now equal to the new node. The new node's next item is equal to the old first item. And then we update pointer first to point to the new node. If that's kind of confusing, we can also make this a little bit longer and we can say doubly linked list node T old first is equal to m pointer first. Doubly linked list node T new first is equal to whatever the new node is. So I'm just creating pointers that point to the same things. Then this basically old first's previous is new first. New first's next is old first. And then we set the pointer first to the new first, which is just the new node. So sometimes if it makes the code cleaner, I tend to like to write code that is easier for humans to read rather than, I'm wasting a slight bit of memory on making some extra pointers, but I don't think that's really a big deal. But for the most part, you will see this implemented, written in the other way here, where we're just thinking in terms of pointer firsts previous is the new node, new nodes next is the pointer first, and then we change the first to the new node. And again, we can reference it either way, and then you can use this to reference as you're working on push back. So let's skip over push back and we'll look at the at a little bit later. Pop front. So this one is going to be for when we want to remove an item from the front of the list. Now, we might have an error if the size is 0, or otherwise if it's empty. In this case, we can throw some sort of error. I have a special structure empty exception. So I'll just use this exception. Pop front cannot pop from empty list. Otherwise, else if the size is 1, well, in that case, we're removing the very last item, so that's another special scenario. Otherwise, then we have more than one item, and this is scenario 2. Let's make sure size is implemented. It is not. This is just going to be returning the item count. So up here, if we are removing the very last item, we erase it, we update these pointers, and then we update item count. So over here, we'll say delete the item at pointer first, set m pointer first to null pointer, set m pointer last to null pointer, and down here we can decrement the item count. Because if it's empty, this will throw and this code won't get executed, that's fine. Otherwise, if we have one item or more than one item, we're still going to want to decrement the item count either way. For scenario 2, again, we're removing the frontmost item, so we have a new first, getting rid of that, and then this has to point at null pointer. So let's go ahead and do that. M pointer first, we're getting rid of it, so we should point it now to the next item. We will delete now the previous item associated with that. And I'll give you another way we can look at this to make it more simple as well. And we set m pointer first, pointer previous to null pointer for safety. So what does that even mean? Well, let's look at this. I'm going to make some more alias pointers. We'll do doubly linked list node t. I'm going to say this one is old first, and we'll do new first. So the old first, we're popping the front. That's going to be m pointer first. The new first is going to be the second item in the list. So that's the next item. Again, we have our first. This is the second item in the list, so this will be the new first. So we have access to those, and we can say the first item is now the new first. We can delete the old first, and we need to make sure that the new first's previous pointer is pointing to null pointer. So again, once we delete this guy, we need to make sure this is pointing to null pointer as its previous item, and then this is pointing here. And you can use that reference to write your push back as well. Okay, with get front, we really only care about returning the data of the frontmost item. However, if the list is empty, that's going to cause a problem. We can't return anything if the list is empty. But otherwise, if it's not empty, we just return the data. So first we'll say if is empty, then that causes a problem. We'll throw a structure empty exception, which is one of my custom exceptions. You could throw perhaps a logic error exception if somebody's calling get front on an empty list. but I'm just going to say cannot retrieve data from empty list. Otherwise, we're just going to return whatever's at the front, m pointer first, return its data. So that's all we need to do there. Let's see. Okay. Now remember, with anything that has to deal with at, we need to have a pointer current and use it to traverse the list. We start at the beginning, we keep going forward until we find where we want to be. So I'm going to actually implement the display function by traversing the list. We need to start at the beginning and go until we hit the end. So we're going to need a doubly linked list node of type T. Pointer current is usually what I name it. And again, that's over there for reference. We're going to assign it to the first item in the list. We can have a counter if we wanted to. For the display, maybe I want to display item number 0, 1, 2, 3. So that would be okay. We'll say counter is 0. And we can say while pointer current is not null pointer, we're just going to go straight to the end. When we get to the last item, its next is null pointer. Or we can check for if our current node is null pointer, then we don't do anything. So while it's not null pointer, we're going to, in this case, outstream whatever the data is. And maybe also the counter value. And then I need to move forward. So as we move forward, the pointer current is pointing somewhere. We just tell it access pointer current's next item to get to the next item. So pointer current is equal to pointer current, pointer next. And since I have a counter, I'm going to do counter plus plus as well. And this will allow us to iterate through the entire list. We could also use a for loop. It's kind of whatever seems more intuitive to you. But basically, if we wanted to iterate a certain amount of times, if this had an index, for instance, we would stop once the counter reached the index, and then we would be at the correct spot. So I'll show you that as well. Let me go ahead and run my unit tests just to see if the ones I implemented are passing. So we'll go down here, look at the unit test result. Constructor's passing, get front, and then these aren't because I haven't implemented them. Is empty, size, push front, that's okay. Those aren't passing because we didn't implement them, and so on. So the rest of them look okay. So let's think about get at. Here's get at. That's my display functionality, but we're not going to keep it quite as is. But we have an index here. We want to get to the nth item of the list or whatever. So basically we can say while counter is not equal to index or less than index. We don't need to do outputs here, but basically we keep stepping forward. This traverses the list. Once we get to where we're at, we are going to return the pointer current's data because we've stepped forward in amount of times, whatever the index is, and return that data. But of course, we also need to check, is the index valid? So is invalid index. If it's invalid, we can throw another exception. Invalid index exception. And I will need to check this as well. Nope, not that part, this one. Yep, that's not implemented. So what is an invalid index? Well, if the index is less than 0, that's invalid. Or if the index is greater than or equal to the item count, then that is also invalid. Because if we have 5 items, the valid indexes are 0 through 4. So item count is 5. 5 is not a valid index. Okay, we can go ahead and run that. Run tests, close that out, refresh this. Let's look for the get at function. And now my unit tests for those are passing. So again, this is how you would traverse it, or you could do something more like a for loop. So remember, with a for loop, we have the initialization action, the condition, and the update. So we could basically just change this around. So we can still do the counter logic. We can say counter is 0, while counter is not equal to index, or while it's less than the index. And then counter plus plus each time. Just move the pointer current right along. And then by the time we get here, we have a valid pointer at the place we wanted. Okay, so given this logic, you should be able to traverse to the node that you need for the push and the pop functionality, but then you'll need to update the pointers like what I showed you with the diagram. So this is kind of a good starting point. Hopefully that kind of shows off how these things would be implemented, and then you can think through how to implement the rest of them. For me, I find it helpful to sketch it out on paper so I can kind of visualize better what I am doing before I get into the code. But if you have any questions about how things are implemented, just let me know.